something is deeply wrong with our best model of the universe, and the James Webb Space Telescope is the reason we now know it. Scientists launched Webb in December 2021 after 30 years of development and $10 billion in funding, expecting it to confirm what we already believed about how galaxies form. Instead, it found something that has cosmologists genuinely alarmed. Within its first year of full operation, Webb detected massive, fully formed galaxies existing just 500 to 700 million years after the Big Bang. That sounds like a long time, but in cosmic terms it is almost nothing. Our standard model of cosmology, called lambda-CDM, which stands for lambda cold dark matter, predicted that galaxies this size simply should not exist that early. The universe would not have had enough time to build them. And yet there they are, 6 of them confirmed in a 2023 paper published in Nature by astronomer Ivo Labb and his team at Swinburne University of Technology in Australia. These galaxies contain as many stars as our own Milky Way, which took billions of years to assemble. Finding them this early is like discovering a fully grown oak tree 1 week after planting an acorn. So what does this mean for dark matter, specifically? Here is where it gets fascinating. Dark matter makes up roughly 27% of the total energy content of the universe. Normal matter, everything you can see, touch, and measure, is only about 5%. Dark matter does not emit light, absorb light, or interact electromagnetically at all. We only know it exists because of its gravitational effects on visible matter. The current lambda-CDM model assumes dark matter is cold, meaning it moves slowly after the Big Bang, and this slow movement is what allows it to clump together and form the gravitational scaffolding around which galaxies build themselves. But if galaxies formed faster than cold dark matter allows, either our timeline is wrong, our understanding of dark matter is wrong, or both. Some physicists are now revisiting a competing theory called warm dark matter, where particles move faster and behave differently in the early universe. Others are exploring something even more radical called fuzzy dark matter, proposed in a landmark 2000 paper and revisited extensively since 2017, where dark matter behaves less like a particle and more like a quantum wave, with an incredibly tiny mass around 10 to the power of -22 electron volts. This wave-like behavior would actually suppress small galaxy formation while allowing large structures to emerge quickly, which fits what Webb is seeing far better than the cold dark matter model does. A 2022 analysis by Glenys Farrar at New York University suggested that if dark matter particles interact with each other even slightly, just 1% more than our models assumed, galaxy formation timelines shift dramatically. Then there is the Hubble tension, a separate but related crisis in cosmology. When astronomers measure the expansion rate of the universe using the cosmic microwave background, the relic radiation from the early universe, they get a value of about 67 kilometers per second per megaparsec. But when they measure it using nearby supernovae and Cepheid variable stars, they get around 73. That gap has now reached a statistical significance of 5 sigma, which in physics means it is almost certainly not a measurement error. It is a real discrepancy, and Webb's early galaxy findings may be directly connected to it. If the universe expanded faster in its early moments than we believed, that would explain both the tension and the premature galaxies simultaneously. The implications are staggering. If lambda-CDM needs major revision, so does our understanding of the cosmic web, the large-scale structure of filaments and voids that dark matter is thought to create. A team at MIT led by Mark Vogelsberger ran new simulations in 2023 incorporating Webb's observations and found that current supercomputer models of galaxy formation fail to reproduce what Webb sees no matter how you adjust the parameters within standard physics. That is a significant statement. It means the problem is not fine-tuning. It is foundational. For you at home, this matters because dark matter is not an abstract concept. Understanding it is the key to understanding why anything in the universe exists where it does, including our solar system, our planet, and ultimately us. Webb is scheduled to operate for at least 20 years, and astronomers expect to push observations back to within just 100 million years of the Big Bang. What it finds in that window could either rescue lambda CDM with some clever modifications or force the most significant rewrite of cosmological theory since Einstein replaced Newton. We are living through that moment right now.